glad to be here and to present on Go in my home country for once. So this is a little bit of a semi-formal, more informal presentation. So if you have questions, please feel free to ask right away. It's also a presentation I've put together over the last couple of weeks only, and it's intended as an overview. So before I start, who of you has already heard of Go or never heard of Go? Let's start with who has never heard of Go. Okay, who has heard of Go and even written code in Go? One person. Okay. Good, so I guess I should dive in a little bit more into details. So let's start with a little bit of history. So what is Go? It's a programming language. It's not a board game. It comes with a lot of documentation. In the meantime, also lots of books. There is libraries and a lot of great tools. And most importantly, at this point, there's a very vibrant open source community. This is an open source project. It has started almost 10 years ago. In fact, September 20th or 21st, I think we started 10 years ago. And as Michele alluded to, it's a 20% project, which is like this fabled concept that we have at Google where every engineer can take 20% of their time and do whatever they want, which is not really true. It's more like if you are burning to do something and you cannot be held back from doing that no matter what, even if you have a day job and you still do it at night, and you can convince your manager that this is something that might perhaps eventually see the fruit of the light of day, he might allocate some time and give you some time so that you can actually pursue it as part of your day job. Okay, but it's not true that every Google engineer just automatically gets 20% time to do whatever they want. So the project started with 3 people, eventually grew to 5 people, and the goal was really to find a alternative to the C++ programming languages. C++ is the most commonly used programming language inside Google, next to Java, and then a whole slew of other languages. Many of us have been programming in C++ for many years. I've been programming in C++ for 10 plus years, and we were sort of tired and fed up with it. And we thought that there must be better ways of doing things, especially in the 21st century. You know, the programming language should not be the problem. It should be the problems you're trying to solve. So that's how Go started. Eventually, in 2009, it became an open source project. We open sourced it. And in 2012, we froze it. And what that means is we decided that we're not going to change the language in any incompatible ways, and we're not going to change the libraries in any backward incompatible ways. It didn't mean we wouldn't make small changes or fixes or add new stuff, but we would guarantee that whatever was there would always be there, at least for the foreseeable future. And that was really probably the most important decision once Go was out, to actually freeze it. That's when all the other people outside in the world, companies, startups, etc., started to jump on the bandwagon and actually use it because they knew they could rely on it. And we've been doing this ever since. We have now a semi-annual release cycle, and in fact, just 4 days ago, we released version 1.9. So that's where we are now. Go 1.9 was released last week. If you look at some statistics that you can find on Stack Overflow, it's the 5th most loved and 3rd most wanted language. It's the number 14 on Stack Overflow in terms of languages used. It's number 9 of languages on GitHub, and it's the 2nd fastest growing. It's number 9 in IEEE rankings. And we estimate between 500,000 to 1 million users, programmers, but that's really hard to get a good grip on this. And it's used all over the place. So obviously there's places like Google, but also IBM, Microsoft, Uber, Dell, all the big tech companies that you'd expect. But then also companies like the New York Times, BBC, but also Amazon, Walmart, and especially in China, it's one of the largest growing languages. We see companies like Alibaba, Tencent, Huawei, Baidu, etc., having large numbers of engineers, but still small compared to the size of these companies, but definitely significant numbers of engineers working in Go and actually doing products in Go that serve real traffic. So if you want to see a little bit more about where Go is in the world and where we are, I highly recommend this presentation, The State of the Gopher Nation by Steve Francha. He gave that last week at the Go conference in London. And it's a little bit more fun and perhaps more sales-oriented presentation, but it gives you a very good idea of how Go looks like in the world, where it stands in the world. So every real project needs a Gopher, and I think I don't know how many percent of the success we have to attribute to the Gopher, but this is our mascot, and this is the one version. It comes in a couple of other versions, very popular, and there's vinyl versions and printed versions and so forth. So let's talk a little bit about the technology. So I talked about the language. So this is a general purpose programming language. It's compact, concise, and readable. What do I mean by this? So compact, it's a small language. You can read the spec, I really mean like the actual technical definition of the language in a couple of hours easily. It's quite readable. It doesn't feel like a C++ reference. The language is concise. There's no public static void main. You just say function main or func main, that's it. And we put a lot of emphasis on readability. So code is more often read than written, and so we really want people to be able to read the code. And you will see that with some of the examples that it looks more like pseudocode than what you would maybe, or some people would consider like software. It's a strongly typed language without the typing, so it's in the tradition of the strongly typed compiled languages, but you don't have to write a lot of type information down. In fact, most of the cases you don't have to write type information down at all, and some of it is deduced. It's a garbage collected language, but it doesn't have the pause times that usually are associated with garbage collected languages. Our garbage collection team has made some enormous progress in that space, and I'm talking here sub-millisecond pauses for very, very large heaps. And finally, it's a scalable and concurrent and efficient language. So this language was designed specifically for large-scale programming development. Think Google style. So there's organization into packages. There's tools that can deal with dependency analysis. Compilers are fast. It's a concurrent language. It's automatic. It supports concurrency in the language in a very, very simple way. And it's efficient. It's compiled to machine code. It runs on a variety of platforms, and it's probably best compared to C. If you will, you can think of Go as a modern C. Syntactically, it has C tokens, so you see curly braces and things like that, but it has Pascal structure, so types are written from left to right as opposed to inside out, which makes them much easier to read. So I don't really have time to go into the details of the language, but I'm going to give you a bunch of examples that pick out some of the things that I think might be interesting to you. So here are a bunch of declarations. Every program in Go consists of essentially 5 declarations. Import declarations, which are declarations of packages you depend on, constant, variable, and type declarations, and function declarations. That's it. There's something interesting about constant declarations in Go. They are actually represented mathematically precise inside the compiler. So if you write down a numeric constant like pi, you can write down 50 digits, and the compiler will maintain those 50 digits, and it will actually do accurate, mathematically precise computation to those 50 or more digits actually when you use those constants. So pi divided by 2 will still be that precise. So especially when you write numerical code, you don't need to write down, this is now a double long floating point number or a double long integer or whatever you have. And then constantly keep in your head what kind of type it is. Constants, if you don't give them a type, are untyped, and they can, again, be arbitrarily precise. So, for instance, the 6th value here, this is really 1/6 inside the compiler, and if you multiply that later by 6 again, you get 1 back as a constant. So it's kind of a small thing, and for the programmer, it sort of falls by the wayside. You actually almost don't notice, but it's enormous when you actually write code, because you never have to think about stuff like that. Then you have variable declarations, of course, with initializations and so forth. There's complex numbers, type declarations, and you can see the structure is like in Pascal. So you have a keyword, you have the name of the type, and you have not a Pascal record, but a struct, C struct. And we have very powerful composite literal constructors. So you can create things like this. You don't need to write functions to create those things. The same is true for arrays and maps and things like that. So it has a very scripty feel. So statements is more C-like, but in contrast to C, there's only 5 binary precedence levels, so you can actually keep them in your head, and you don't have to put in parentheses just because you're not sure if it needs one or not. We got rid of extra parentheses around if statements and stuff. We got rid of semicolons where we could, but we made curly braces mandatory. And so as a result, an if statement looks more like this. So no parentheses around the condition, but these curly braces are always present. And we allow initialization expressions in an if statement, same as they are already in a for statement, same as they're in, and you can also do them in switch statements. We have parallel assignment, so if you say x comma y equals y comma x, that's a true parallel assignment. That swaps actually the two values. It's kind of useful. Switch has been fixed, so you can write things like this. The break is implicit. Common sense things that were clearly, I would say, broken in C. So there's functions, of course. They look like this. Here's a simple function that computes a minimum. They are first-class objects, so they're closures. So you could write the closure like this here without the body, assign it to a variable f. And we have a very clean handling of variadic signatures. It's built into the language. There's no macro stuff going on here. And inside this function, you can access these arguments as if they were like part of an array or slice. There's an easy way of declaring a new variable, and giving it a type and assigning a value to it here. We see x is declared as a new variable, and it gets the type of this function result and is initialized to the value that this function gives you. And so this is one of the small but powerful things that make Go so easy to use, because you can declare variables very quickly. You don't need to write down a type, and you get everything there with a few keystrokes. So I tried to find some numerical application. So here's a mathematical matrix multiplication. Of course, this is like not how you would do matrix multiplication in your field. I'm aware of that. This is like a textbook multiplication where you just have these 3 loops that iterate through it. But I want to show a few things here. So Go is an object-oriented language, but it's not object-oriented in the same way as, you'd say, Java is, or other languages. There's no classes. There's no subclasses. There's no inheritance, things like that. What we have is we have 2 concepts. We have the concept of methods, and we have the concept of interfaces. A method is simply a function that has a receiver. And so here we have a function called at, and it has an argument that is before the function name here, and that is the receiver. Some of you may have heard of Oberon, one of the last languages that Niklas worked on. Oberon 2 had exactly this kind of notation, and that's where it's coming from. And what this means is that this is now a function or a method that is bound to this type. And so inside this function, you have access to, of course, this matrix via this additional parameter here. And this is statically bound. So there's no difference between a function and a method in terms of execution at this point. This is simply a notational convenience. And it allows you to call this function via a method call. I've not said that in the beginning, but Go has not been designed with scientific computation in focus. So there's some things that from a scientific computation point of view, you might find lacking. And I'm going to address this a little bit. I'm trying to address this a little bit. Specifically, there is no multidimensional matrices. There's very strong support for one-dimensional growable arrays, which we call slices, but not for two-dimensional things. And so one way one can work around this is by actually implementing an accessor yourself. So that's what I've done here. And then I've written a matrix multiplication in terms of this accessor here. So I'm just calling this function or method, I'm calling this method, and this is the equivalent of the statement if you had that kind of access. So again, coming from the C tradition, it's not something that's there automatically. So object orientation is achieved by the concept of an interface. An interface is a type that simply defines some methods. So it's very similar to what you might see in Java and other programming languages. But the difference here is that you don't have to specify first this interface implements another interface, or this type implements this interface. The connection is implicit. Basically, if you define a type that has a certain set of methods, and if those methods happen to satisfy the method of an interface, then that type satisfies that interface. So here is a very simple example again. So here's an interface that defines a new method string that produces a string. And now, if I'm going back to the matrix type that I had before, if I define a method string on that matrix type, then I can assign this matrix type M, a value of that matrix type M, to a variable of type stringer, even though these are different types. This is an interface, this is a matrix type, but this matrix type has the same method string as the interface type, and so I can do the assignment. And then I can call x.string, and in this situation here, this is the place where dynamic dispatch happens. So this is the string method that belongs to the type that was stored in X. So it's a matrix. If I store something else in there, then the corresponding string method of that type will be invoked. That's really all there is, and it turns out it's incredibly powerful. And in contrast to other languages, we cannot just give methods to records or classes. We can give methods to any type. You can define any type and give it methods. It could be even an integer type or a floating point type. And finally, there is concurrency. So in Go, there is two concepts. One is the concept of a Go routine, and one is the concept of a channel. And we call the coroutines Go routines, of course. And a Go routine is being launched by the keyword Go. So if you have the keyword Go followed by an ordinary function call, then this function is going to be launched as a Go routine, and it's going to run concurrently with whatever else you have running. Specifically in this case, it would be running concurrently with the code that launched it. And at that point, that thing is out of your direct control. And that's all you need to do. It's really technically just a coroutine. Now, once you have a coroutine launched, of course you want to communicate with that coroutine, and that's where channels come into play. A channel is a type. You write down like this, channel of T. T can be anything. It could be a struct, an integer, whatever we want, a string. And channels are essentially pipes. Think of it as a Unix pipe. You can send to a channel and you can receive from a channel. And when you send to a channel, the channel is blocking until somebody on the other side receives. And vice versa, if you receive from a channel, it is blocking until somebody actually sends. And so that's where synchronization happens. And so if you have multiple, thousands typically of coroutines launched, then they are usually communicating through channels. So here's an example of how that would look like. So you would create a new channel. It's a channel of integers. And so this is the statement that sends the value 1 to that channel. And if nobody is reading from this channel somewhere else concurrently, then this statement will be blocking. And here again, here you're receiving from the channel and store the value in the variable x. And again, if nobody is sending on that channel at the same time, then you will be blocking. So channels are a way of communicating. And Rob Pike, who is one of the co-creators of Go, has this famous quote here, is that don't communicate by sharing memory, share memory by communicating. So the idea is really that when you have to communicate across several coroutines, that you should use a channel to signal this piece of memory. It doesn't necessarily mean you have to send all the data over the channel, because that would be an expensive operation. But it's enough to signal over a channel that now this data is, for instance, ready, and then another coroutine has access to that. It's important maybe to say that there's no protection of that memory. So there's no. It's not like an Erlang process where once you launch another process, that process is basically walled off and you have no access to it. And the reason is because we want to be efficient. And this turns out actually to be a paradigm that works extremely well. So in Go, a coroutine uses very little memory. I think it's 4K. So it's no problem on a modern laptop to launch 1 million coroutines in less than a second. And it's easy to communicate between them. It's very, very, very efficient. So I'm taking this and I'm going to go back to the matrix multiplication example and exploring this a little bit. So I rewrote this function before a little bit. It's still not, what you would write, what you guys would write, but it's perhaps a little bit better. So instead of doing my 3 loops here, I now replace the inner loop with a dot product between a row and a column. But I also want to access the data in the memory in row major order, because memory is stored in row major order. So I take the first matrix, that's A, and then I take the second matrix and transpose it, so that's T. I create a new matrix for the result, that's C. And then I'm going to iterate over the A rows, and I'm iterating over the T rows, which is the transposed B matrix, and then I just do the dot product. Okay. So that's your new matrix multiplication is not using concurrency. And now I made an experiment. It's literally a 5-minute experiment here. I took this piece of code and I wrote it using concurrency. Okay, and the idea is that I'm just going to run this inner dot product concurrently. And so how much work do I have to do? This is the amount of work I have to do. Okay, so first of all, I'm putting the inner body here into a closure, this function here. And I'm launching this as a Go routine with the Go keyword. I have to pass in a bunch of parameters because while this thing is running, these values A, I, and J outside change, because this Go routine is now off on its own, so I need to pass them in. So that's really launching the Go routine, and that's all that there is to be done to make this concurrent. But I also have to make sure that the outer function doesn't just return while all these coroutines are still running. So there's a little bit of machinery around it. Don't go too much into detail, but essentially I'm declaring here a wait group, which is a mechanism that allows me to wait on something. And specifically, I'm going to wait for m times n dot products. Okay. And the way I'm waiting for them is with this call here. And finally, inside the closure, every time I've done a dot product, I say done. Think of this like as a semaphore with a counter. So every time I'm done, this call wait group done signals to this group, okay, one less. And eventually we'll reach 0, and that's when the wait group wait here will unblock and continue. So this program now does exactly the same thing as before, but it launches basically m times n coroutines and tries to run them all in concurrently or in parallel, which of course they're not going to run concurrently, in parallel on my laptop, because this is only like a, I don't know, 2-core machine, maybe with 2 hyperthreads, so it's maybe 4 cores, but still. So I ran this and I wrote a little program, a little wrapper around it that multiplies first 10 by 10, 20 by 20, and so forth, up to 1,000 by 1,000 matrices. It just does the matrix multiplication once in the very old way, once as a dot product, and once concurrently. And that takes a little while because it has to compile, and now it's running, and you can see n is the size of the matrix. And there's 3 results. Mal is the original school book matrix multiplication. Mal fast is the same, but using a dot product. It's faster because it can do fewer array bounds checks. It's faster because it can access the data in row major order. And then the last one is concurrent. And this is, of course, a toy, but you can see this 5-minute operation using some concurrency here reduced the computation time by a factor of 2, even more. So for 1,000 by 1,000 matrix, it's about twice as fast concurrently than not. And so that's pretty decent. So this is 1 billion multiplications. This is not a super fast machine, but it's kind of in the right ballpark, less than, a little bit more than half a second. And this is something, literally takes you 5 minutes to do. There's almost no thinking involved. Yeah?
Is Go kind of noticing that it's oversubscribing the processor, so it doesn't really spawn a new OS thread?
Yes, so this program is really done. Okay. I'm really launching, 1 million coroutines here, and they're all waiting. And then, there's probably 4 that can run simultaneously, so they're going to run, and then the next one is going to run, and the next one is going to go on, and so forth. So I could be much smarter, and I could, first of all, probably use a higher granularity, not a single dot product, but maybe like, 100 dot products. I could only launch 4 coroutines, reduce the overhead of the coroutines, and so forth. But yeah, it just puts them aside.
So those are actual threads?
Pardon?
They are actual threads?
They are actually, they're not threads. The coroutines are put onto threads.
Okay.
Because if we would use threads, we could not launch 1 million. Okay, any other questions on this? Okay. So the previous few slides, I tried to give you a little bit of an idea of what's there in terms of language. Okay, there's lots more to talk about, but I don't really have time to fill this talk just with language details, and it probably would be too boring. So I'm going to talk a little bit about the other aspects of the language. So I mentioned before there's a standard library. It's very high quality. It also has this 1.0 guarantee. That means we're not going to make changes that are backward incompatible. We're making small changes to fix things. We made a lot of changes in terms of performance and so forth. It's platform independent. It runs on a variety of machines. And it contains the usual library stuff. that you would expect, but it also contains things that are not traditionally part of a standard library, such as tools to manipulate the language itself. So for instance, there's a complete parser for Go programs. There's an abstract syntax tree as a library. There's tools to manipulate the abstract syntax tree. There's a printer, which allows you to reprint it. And there's a type checker that is not part of the compiler. It's outside, so allows you to take a Go program and type check it, and then have that information to you available as a data structure. And so this has opened a whole new world of tools that people have written. The most notable one is the one that was there from day one, which is Go font, which is a formatter for Go software. And at this point, it's fair to say that probably 99.9% of all Go code that's out there is formatted via Go font. It's just a source code formatter, but it actually takes care of comments, and it does a fairly decent job. So people have sort of converged on the style, and as a result, when you see Go code out there, it pretty much looks fairly uniform, and you can read it. You don't have to get used to somebody else's, ideas of where a curly brace should be and so forth. I'm going to show quickly here the library. Let me see if I can make this a little bit bigger. So this is sort of what is in the standard library right now. So you can see, I'm not going to go into details, but just give you sort of an idea. What there is, there's compression stuff, there's containers, there's a lot of cryptography. It sometimes feels like the world is only about cryptography these days. Encoding stuff, then what I mentioned before, a lot of libraries that have to do with the language itself, hashing, HTML, I/O, some math stuff, a lot of networking, including very strong HTTP support. In fact, part of the library is an HTTP server. If you wanted to write a simple HTTP server in Go, it takes about 5 lines of code. The usual stuff, operating system stuff, runtime stuff, string things, and so forth. This is a standard library, but in the meantime, there's a slew of other libraries out there. Implementation-wise, so I mentioned this is compiled to C, statically linked by default, which is actually one of the reasons why Go is so successful, especially now, where everything is being containerized or put into the cloud. People really like that the binary is statically linked. There's just no deployment issue. You have your binary, you put it on the machine, and it runs. If you come from Java, it's a nightmare. You have to make sure that you have the right JVM installed, the right libraries, the right flags, and so forth. Same with Python, same with a lot of other languages. So this is like, this is just huge. It's a default. You can do some dynamic loading, but that's the default. We have a runtime. It's a compiled yet garbage collected language, so we need a garbage collector. So there's a runtime that's automatically linked in. It also deals with the scheduling of the Go routines and so forth. We have 3 compilers. Command compile is the one that's the native, so to speak, compiler. It's written in Go now. But we have 2 others, GCC Go, which is an implementation of Go on top of GCC, and a more recent effort, Go LLVM, which is based on LLVM, which is not that far ahead. And it's supporting a lot of operating systems, and it's supporting a lot of architectures. And it's fairly easy to do an import. So here I can show you our actual honest to God build page that, where you can see what happens when you submit. So we tested on all these architectures, and at the top here you see the various operating systems. So Darwin, FreeBSD, Linux, and so forth. And then there's it's probably hard to see here, 386, 64-bit machines, and so forth. Then there's ARM, ARM 64, There's PowerPC, there's even an S3, IBM 390 that's supported. And a lot of these ports actually have been done by the open source community. For instance, the Windows port has completely been done outside our group, outside of Google, in fact. We have a lot of sub-repositories which are also being tested. Whenever somebody does a commit, we can, we test on all these platforms. We run an extensive test suite. I briefly mentioned garbage collection before, so here is a quote. This is fairly recent because we just released 1.9. This is the release candidate 2. And this person, which is running a significant service, is using Go, and they see sub-millisecond pauses. That's where the system stops for a heap that is 18 gigabytes, which is fairly large for a web service. So other languages don't really get quite to this short pauses. I mentioned tooling, so we have a build system. So if you write your code all in Go, you actually don't need to write a make file or anything like that. You just point your Go build tool into the directory where you are and say Go build. And it will read all the files in that directory, and it will automatically figure out the dependencies, because in Go dependencies are explicit. If you say I'm importing this, then you've written down your dependency. And we have a somewhat canonical organization of directory structures which allows build tool to figure out where it needs to find its dependencies. I mentioned GoFont. There's a documentation tool similar to JavaDoc. There's a vet tool that checks a lot of things that the compiler maybe cannot check because it's not part of the language specification. For instance, did you provide all the arguments to a printf? Did you provide the right types? And so forth. Did you shadow a variable that you were not supposed to shadow, and things like that. But then there's a lot of other very interesting tools, like a coverage analysis tool, which automatically checks whether your tests cover or how much they cover of your code. There's a race detector, which is enormously useful. There's benchmarking support, and so forth. Here I can show you the GoFont briefly. This is the Go playground, where you can write a piece of code and just run it on the web. You don't have to install anything. This is a piece of code showing the stringer example again, but it's not very well formatted, maybe a little bit hard to read. And so you can just click on, in this case, format, and puts it into the canonical form. And of course, you can do this for large programs. It's just the easiest place to show it here. Since we're here in the playground, you can also run this. Okay. Maybe, yeah. So, I'm not going to go into details here, but. So, Michele asked me about things like interoperability. So, that's, of course, if you have a heterogeneous system, which is a lot of people have, you want to be interoperable with C. Now, Go is a garbage collected language, so there's always issues when you go across that boundary because you have pointers, etc. But in Go, pointers are not moving. The garbage collector is not a moving collector. So you can, in fact, pass Go pointers into C with some care, as long as you make sure that they stay alive while you're in C land. And the overhead is much less so than if you would use something like JNI in Java, where you actually have to go through a little dance, or JNI has to do a little dance to make sure you get the pointer across. And then you have to use a handle. The basic idea is this. In Go, there's a special sort of magic import C. And if you have an import C, all the commentary before the import C immediately adjacent to that C can be some form of stylized C code. And then you run it just through the ordinary Go compiler, and it will automatically extract this. It will automatically construct Go wrappers and automatically do the right bindings, and the linker will then connect it. And then you can call these C functions as such. So you could say c.intfunc would, for instance, call this thing. No, this is a cast, sorry. 42. So c.42 would, for instance, refer to this function. Okay. And then you cast it into this type and so forth. So you can do quite a bit with CGO, and it's pretty efficient.
You call functions that you haven't included in. I mean, do you have to include all the C code in this little?
Well, the typical, usually you wouldn't do it this way. You would include something. Okay, you write an include statement.
Okay.
And so typically you'd have some header that's written somewhere else, and you just include that header. Okay, so it's not like you have to write everything.
But I mean, if your header included lots of C code and you had a huge library written in C and
right.
you had a few entry points that you wanted to call,
right.
That's okay, as long as you stick to a limited number of entry points.
I believe that's okay, yes. So I have very limited experience myself with this API. I've done it, and it works, and I know there's a lot of people that use it, and I'll get to some other examples. Yeah?
What about the C++ group?
So it's C. So the problem with C++ is that there's mangling of the names in C++ due to the typing, and so it gets more complicated. So as long as you sort of interact with the C subset, so to speak, of C++, you're probably okay. But again, I'm not if this is something you'd be interested in, I can connect you with the person that's written the code. I'm not very familiar with this. I've just not done it. So I mentioned in the beginning, scientific computation was not the primary goal focus when we were working on Go. So there's no direct language support for things like this. There have been various proposals being made. In fact, there's a fairly active community that they call GoNum people who have worked on various proposals, and they also have written fairly extensive libraries. And I mentioned a few of them here that support some of the standard stuff like the LAPACK libraries and so forth, which can be accessed through these libraries from Go directly. And so these are essentially wrappers. There's even an MPI library, which I just found out. I've not looked at any of these, so people have started working on these kind of things. So last but not least, Go has become fairly big in the last few years. There is a lot of conferences at this point. There is, since 2014, there is a regular annual Go conference in Denver, which is called Go4Con, and at this point attracts probably 1,500 people. I haven't been there this year. It's usually in July. There is a Go conference in China. Was in Shanghai in 2015, and I think in Beijing last year. Since a couple of months, there's a Go4Con in Singapore, which attracts all the people from the Southeast Asian realm, which is exploding in terms of startups and things like that. There's a regular conference in India, there's one in Brazil, and then there's various smaller ones like .go in Paris, and so forth. And there's a lot of meetups. So a lot of cities have regular meetups. There's one in Zurich, I know, was just like a couple of weeks ago. And they usually meet like maybe once a month or so. People from the Go community, there's a short number of talks, maybe 20-25 minutes, and people can discuss their problems. Yeah, I mentioned that. So where are we going? So we have some near-term goals. One of the things that we hear from the community a lot from industry is we need to have better dependency management and versioning. That's a big thing. We have some dependency management solutions, but versioning is not, there's not much there in terms of versioning. There's some outside tools, but we are trying to consolidate a little bit. We are working on a new user experience, meaning our web page has now been unchanged for several years and looks a little bit stale at this point. Probably needs to be, we're in the process of revamping it. And we also are working on improving our community culture, as many of these projects have a little bit of a problem of not feeling very inclusive, even though that was not really the case with Go. But we're trying to get more diverse group of people into, feel welcome. And as part of that, for instance, we launched a code of conduct a couple of years ago, which has been very successful. We have more women now that are contributing to Go. We want to have more different people. So that's kind of like on the sort of outside, face of things. Internally, we're working on faster compilation, better code generation, better libraries, and specifically Go 2. So in about 2019, in 2 years, Go has been open source for 10 years and has, as a language, not changed a whole lot. That's 10 years, and 10 years is a good sort of milestone after which it's probably time to think about what we've learned, what we've done wrong, what should be improved. And so we call this Go 2, the next generation of the language. And it's not clear what's going on in there. We're trying to keep it simple. That's something that people like. But we're also trying to address some of the things that people are missing. And we're, as a company, we are making a big push for Go as the language for the cloud. It's very successful in the cloud, but we're trying to sort of ride that momentum and really make it the language for the cloud. Because a lot of the cloud systems that are out there are really based on Go. Okay, that's it. Hope that was helpful. Thank you very much. Happy to take questions and go into details.
Okay, thank you very much, Robert.